Welcome back to the channel, everyone. Before we dive into today's lesson, please make sure to smash that like button, subscribe to the channel, and follow the account so you never miss an update on our A+ certification series. Today, we are talking about the lifeblood of the PC. Every single component we've discussed so far relies on a constant, stable supply of power to survive. The power supply unit, or PSU, is the ultimate protector and translator, converting raw, chaotic electricity from the wall into the refined energy that keeps your entire system alive. Raw electricity must undergo a rigorous journey before it can safely power sensitive electronics. Think of this in 5 distinct steps. First is the source, acquiring raw AC power from the wall. Second is capacity, managing the total wattage payload of your hardware. Third is transformation, converting that AC power into DC power efficiently. Fourth is refinement, splitting that DC power into precise voltage rails. And finally, delivery, routing that power safely to the motherboard and peripherals. Let's look at the source. Scenario: you are deploying identical server racks in a North American branch and a European data center. Before power can be transformed, the PSU must handle the wall input. You must ensure the PSU matches the regional alternating current, or volts AC. Low line is 110 to 120 volts AC, which is standard for North American wall outlets. High line is 220 to 240 volts AC, standard for international outlets and high-efficiency data centers. The savior here is that most modern PSUs are dual voltage and will auto-switch. The danger? Legacy PSUs require you to flip a manual switch. If you plug a fixed 110-volt adapter into a 220-volt supply, you will cause immediate, catastrophic hardware damage. Next is capacity. Scenario: you are building a high-end 3D rendering workstation with multiple graphics processing units, or GPUs. The PSU must meet the combined wattage requirements of every single internal component. A standard desktop needs about 400 to 500 watts. A gaming PC requires 600 watts or higher, and an enterprise workstation or server will draw 1000 watts plus. The risk here is starvation. An underpowered PSU starves the system, leading to random reboots, system instability, and permanent component damage over time. When transforming AC to DC power, we have to talk about the cost of inefficiency. Scenario: a corporation wants to deploy 500 new desktops while minimizing ambient office heat and reducing their electrical bill. As the PSU converts power, excess energy is lost as heat. For example, a 300-watt PSU operating at only 75% efficiency will actually pull 400 watts from the wall outlet. That wasted 100 watts creates higher energy bills and forces the system's cooling fans to work significantly harder. To guarantee energy efficiency, we look for the 80+ certification. This standard ensures a baseline of at least 80% efficiency at 20%, 50%, and 100% load capacities. The ratings scale up through bronze, silver, gold, platinum, and titanium, which hits up to 94% efficiency. The result? Lower energy costs, drastically reduced heat output, and a significantly longer lifespan for the surrounding components. Now we refine the flow. Inside the computer, components require different flavors of low voltage direct current. The PSU splits the power into specific output rails, utilizing voltage regulators to ensure absolute consistency. The 3.3V and 5V rails power smaller logic circuits, solid-state drives, and peripheral devices. But the 12V rail, that is the heavy lifter. When evaluating power distribution, the Pluzin 12 VDC rail is the single most critical metric for modern computers. This rail carries the heaviest load, supplying massive amounts of power directly to the system's most demanding components, your CPU and your PCIe graphics cards. When you are calculating power for a heavy-duty scenario, the maximum output on that 12V rail dictates your entire system's stability. Let's move to delivery. Scenario: you are replacing a dead power supply in an older office PC with a legacy motherboard. The primary connection to the motherboard is the P1 connector. The legacy standard utilized a 20-pin block. The modern standard requires a 24-pin block to handle increased power demands. The solution? Most modern PSUs include a 20 plus 4 pin adapter. Those extra 4 pins can be snapped off or left unattached, giving you absolute compatibility across both modern and legacy motherboards. When architecting the build, cable management matters. Scenario: you are building a high airflow, thermally optimized system in a compact chassis. A standard power supply has every possible cable permanently attached. If you don't use them all, you are left with a massive nest of unused cables cluttering the case and choking your airflow. To solve this, we use the modular advantage. A modular power supply features a back panel of empty sockets. The technician attaches only the exact cables required for that specific build. This provides zero clutter, eliminating the need to hide unused Molex or SATA connectors. It offers thermal superiority by radically improving the internal airflow of the chassis. And for maintenance, replacing the PSU is significantly easier, as the routed cables can simply be unplugged right from the unit itself. But what about servers? Scenario: you are managing an enterprise database server where even a minute of downtime results in catastrophic data loss. Standard desktops can tolerate being powered off for maintenance, but enterprise servers cannot. To guarantee continuous uptime, these systems utilize redundant power supplies, two identical PSUs installed in the exact same chassis. If one suffers a mechanical failure, the failover redundant supply immediately takes the entire load with zero interruption to the system. So, how do you replace that dead power supply without turning off the computer? You use hot-swappable guardians. In a redundant setup, the PSUs do not plug directly into the motherboard. Instead, they slide into a specialized circuit board called a backplane. This architecture allows the PSUs to be hot-swappable. A faulty unit can be physically unlocked, pulled out, and replaced with a new unit while the server remains fully powered on and operational. From the wall to the motherboard, you now control the entire journey of power. You know to match the 110-220 VAC to the environment. You calculate wattage and rely on 80 plus efficiency. You distribute that critical 12V output. You connect the 20 plus 4 pin main artery, you optimize airflow with modular cables, and you protect enterprise uptime with redundancy. Every hardware failure is a mystery, and every deployment is a new challenge. By analyzing the specific constraints of the environment, the demands of the internal hardware, and the uptime requirements of the user, you are now fully equipped to resolve any scenario. You hold the lifeblood of the system, and you know how to install the perfect power supply. To lock this knowledge in, make sure to finish your study session today by getting some hands-on practice with PBQ-like questions at XP Boost. Thanks for watching, and I'll see you in the next one.